Welcome to the next lecture series of the ongoing course Perception Algorithms for Autonomous Systems. In this, so far we have started the heart actually of the perception system, that is the estimation and tracking along with sensor fusion. So, we completed least square technology methods, we completed Kalman filter, detailed we have done the Kalman filter. We took an example of a Kalman filter on a vehicle collision avoidance systems. Then we started basically the extended Kalman filter when your system is dynamics is nonlinear, how to use it. We took a sinusoidal state estimation, signal state estimation problem, and we demonstrated how EKF is behaving, first order EKF. Next, now we will be in our nonlinear filtering series. The next thing which is very important, almost kind of a very important stuff for target tracking application is called pseudo measurement conversion or coordinate conversion approach. It is alternatively it is known as pseudo linear filtering. So, basically you have a nonlinear system, a nonlinear measurement dynamics, you convert it into the linear system, linear measurement dynamics, estimate your, so your H matrix will change, your covariance from a nonlinear measurement error covariance, you have to convert it to linear measurement error covariance, and then you apply your normal linear Kalman filter. So, this is very important in target tracking, and almost each and every modern radar or UIR or any kind of RF detector sensors uses this pseudo linear conversion technique. It is very popular than extended Kalman filter. With this, first let me start with two examples first. So, there is no theory, it is all example and some basics your statistics or maths, that is all. So, we take an example of a 2D radar tracking problem where actually there is a radar. So, radar is normally, as I discussed during my measurement model lecture, giving you polar measurement, say it is a range and azimuth or bearing angle. So, range and azimuth, as you see, it is r and theta are in polar coordinate. So, if you see this, so this is your actually will be your r and this is your azimuthal plane, the angle is theta. So, this is the polar form, we need to convert it into Cartesian form. So, your x will be equal to r of cos of theta sorry, y equal to will be r of sin theta. This simple polar to Cartesian coordinate conversion. So, we did it here. What is XR YR? XR YR is your sensor location, sensor coordinates, where your sensor is sitting. Say your radar is sitting say here. If it is say at origin, then XR YR will be 0. Okay. R is your radius, theta is your azimuthal angle. Now, I would like to now see when we have my sensor is giving me r and theta, rm and theta m. So, you have obviously your sigma r and sigma theta, this is also will be coming from the sensor measurement. When you simulate your sensor measurement, actually you will get these two quantities, your measurement error, standard deviation. Okay. So, they are on polar coordinate. Now, I want to use pseudo measurement filter. So, my state model you can assume it is 1t01. So, your constant velocity model, it is a linear model. Measurement is nonlinear. So, from nonlinear I converted into x and y. So, that is why it is called Cartesian coordinate tracking. What is Cartesian coordinate? Because I am tracking my state is in Cartesian. My measurement was in polar, so I changed from polar to Cartesian. So, ultimately I get Cartesian measurements xm, ym. Now, I have my measurement error variance, that is the Kalman filter R matrix. They are usually in polar coordinate, obviously it will be in polar coordinate. So, I need to convert it from polar measurement error covariance 2×2 matrix to a Cartesian 2×2 matrix. How to do that? To do this, what is the delta x and delta y in xm and ym, that I will calculate. It is simple, it is a first order Taylor series kind of your Jacobian. You can tell it's nothing but a Jacobian, not kind, it is a Jacobian only. So, delta x, delta y, you can find out delta xt by delta r, delta xt by delta theta, delta yt by delta r, delta yt by y theta. And if you do the simple differentiation, you get this is your error. Okay. Once you get the error, now you find out statistics. Enforcing there is everything is Gaussian. And when you enforcing your statistics, because Gaussian assumption means first order and second order statistics. So, when it is a first order statistics, obviously you can, it is a mean. So, mean value will be 0 under 0 mean wide Gaussian noise assumption. So, obviously you can safely assume that expectation of delta r 0, expectation of delta theta is 0. And when you calculate the covariance, so covariance when you calculate, you have to condition it in truth value. Now, since truth is not available, so how you will do? Either you have to convert on estimate, predicted estimate, or using, because that is the only thing you have at that time, at time instant, or using the measurement, anything. But normally we do it using estimate only. So, once you do, so you get delta x is this whole square term, and you get like this. So, now you calculate expectation of delta x t square. What you will get? Since it is conditioned on predicted or truth or predicted, whatever you see, cos square theta will come out. So, your expectation will be this much, delta theta r square, expectation of delta r delta theta, expectation of delta theta. Rest all things are predicted value. So, they are constant, you can take it out safely. Okay. Now, expectation of delta r square is your sigma r square, expectation of delta theta square is your sigma theta square, and since it is a Gaussian assumption, delta r delta theta are uncorrelated to each other. So, obviously, cross covariance will be delta r delta theta will be 0. So, this term vanishes. So, ultimately, you will get actually in the first expression, if I rub this, if I rub it out. So, first expression actually you will get sigma r square cos square theta plus r square sin square theta into sigma theta square. Okay. So, this is the first thing that we will be getting. Similarly, we solved for delta y t square, you will get another expression, and most and very important thing is that this time this fellow will be coupled. So, your delta x delta r delta theta is not coupled, but since you are multiplying it, you can see there are certain delta r square term is coming, delta theta square term is coming. Anyway, this term will be going to take expression, they will vanish, not an issue. But because of these two terms, your Cartesian will be coupled, polar is uncoupled. So, there is no off diagonal element, but Cartesian will be coupled. So, once you solve, you get this is your sigma x square, this is your sigma y square, this is your sigma x y. So, that is what all I just told, it is written here. Okay. And you can have your R matrix now coming like this. Now, again I am telling R matrix is derived condition on truth. Since truth is not available, what is available? Is my truth means now I have only predicted estimate or I have my measurement. Either one I can calculate R. Normally, we do not use measurement because measurement is still erroneous, because predicted is the your by and by the more refined measurement. Okay. So, normally this R matrix is estimated on predicted. So, each and every dt your R matrix is going to be adaptive. In Kalman filter R is constant, but here now R will be adaptive in nature. Each and every dt your R matrix is going to change because of your theta predicted and R prediction and theta prediction. Okay. So, R pred will be R of k minus 1. If I say this will be actually your x of k minus 1 square plus y of k minus 1 square, theta will be arctan y of k minus 1 divided by x of k minus 1, right. So, this is actually your theta predicted. With these two things, now you put it into R, and each and every dt your R is going to be updated during your after your prediction cycle in the measurement update cycle. So, that your Kalman gain will be varying change. We will take an example now, very simple example. Again I have taken a linear target is moving in a linear motion. So, A0 plus A1t, and we already derived all this equation previously. So, that means my this target is having two state, first order filter, it is a first order filter means two state. Okay. So, one is your position, one is your velocity. So, two state, position and velocity. Okay. And you know that x and y is related to x and x dot, and y dot are 1 t 0 1. So, your final state transition matrix will be 1 t 0 1 is for x dot, y dot. When you x y motion I have assumed to be uncorrelated, 0 2 cross 2 matrix, 0 2 cross 2. Okay. So, this is going to be your state transition matrix. Okay. Now, you have the same radar 2D plane measurement r and theta. Okay. You have done this conversion and all. Now, this is your actually algorithmic stage, how your pseudo-linear filter, it is just a Kalman filter. You are running a Kalman filter, only thing you are updating your covariance, a measurement error covariance each and every dt. So, you start run filter with your x0 p0. You have to choose a right initial guess. You go for time update. What is time update? Kalman filter does your state update and state error variance update. Okay, predicted state error variance. So, predicted state means phi of xk minus 1 you have to do using your state transition matrix, and what is your predicted state error variance? It is actually phi p kk minus 1 phi transpose plus process noise covariance, that will give you a predicted state error covariance. You got it through time update. Now, you calculate your predicted Cartesian measurements. So, you have your now r and so you have now your x and x k k minus 1, y k k minus 1 predicted values are there for x and y. You calculate your theta and r, already I have shown you how to calculate it. So, you can see it here, this is your r and theta, you have x and y, you can calculate your range and bearing. You calculate it, then actually once you calculate, okay, I have written it 2 times, just ignore it. So, straight away you can come here. Okay. Next is calculate Cartesian converted measurement error variance using predicted state. So, from here directly you can now calculate your r, obviously all these equations, your equations are already given, this is your r matrix. Once you have r hat and theta hat predicted, you can calculate your r, sigma theta, you know, using this expression. So, you calculate your r, you go your Kalman filter measurement update. Measurement update means first is calculation of Kalman gain. Kalman gain is what? Output covariance into innovation covariance inverse. Here what will be your H matrix, because you are now using a linear measurement. So, actually it will be 1 0 for actually 1 x and x dot, and for y and y dot it will be like this. So, 0 0 0 0 1 0, it will be something like this. So, your H is linear matrix. So, P into H transpose is your output covariance, you get it. Innovation error covariance H P H transpose plus R, yes, you can get it. H you know, P you know, H R you have calculating here, you can get your Kalman gain, and now update your state for estimate your state and estimate your state error covariance. Okay. And then your cycle is repeating. So, this is actually very important for the thing that for in the how a pseudo linear filter works. So, here the difference between a linear filter or an extended Kalman filter is that you are using a linear filter, only your R matrix is going to be updated each and every time. Now, see what I have now, there is an important thing, my states are x dot y dot, and my measurements are now xm ym. So, that is why I have able to rewrite this linear matrix, linear H matrix. Okay. Otherwise, I could not have write, because I want to bring my measurement should be a function of my state. If I make it linear function, not a non-linear function, if I make it, then only I can use a linear filter. Otherwise, I have to go for EKF and all, if this is possible. Pseudo measurement is not all the time possible. Tracking, however, for radar tracking, yes, it is possible to some extent. UIR tracking also, there is a way to calculate your x and y. But normally any kind of nonlinear process or nonlinear thing, it is difficult to estimate this pseudo measurement, because to get a linear function and all, sometimes it is difficult. Okay. But fortunately, since we are only concentrating on target tracking, our Kalman filter is only related to target tracking. In our application, it is easier. I will now tell a very important thing, what is called filter initialization. So, as you have seen here, that I am initializing filter, because without this my filter won't work. Okay. How to initialize it properly, or I can do it in the name of tracker initialization. Tracker as what will be my initial value of my position and velocity on x direction and y direction. Simple. Normally, there are 2 ways to estimate, to kind of initialize. When you do not have, say, any knowledge in truth, actual in physical system, how the in physical radar tracker, how it is kind of implemented. Here it is implemented using measurement based initialization. So, you use your first position measurement or second position measurement to initialize your x or y position, x and y. So, here I have used the second position measurement. Why I have used second? I could have used first also, I will tell. So, why I have taken here second position measurement to initialize my filter position, and the velocity I have done a 2-point differentiation, simply delta x by delta t I have done. So, that is why I have taken second, because then otherwise I could have taken 1 here directly, you can assume. So, velocity is in a 2-point differentiation method. Okay. Once I do this, it can be statistically proven, it is very easy, it will be part of your assignment. What will be my initial P0? Initial P0 first diagonal element, that is the position error variance, will be sigma x square. So, that means converted, when you are converting it using your R matrix, you are calculating it using your measurement. So, that will be your first error covariance. Okay. Cross covariance, there will be cross covariance also, since it is x and x dot, there will be cross covariance. So, that is sigma square t, and velocity error covariance is this 2 sigma x square by t square, and same thing propagates for y direction. Now, there is a question. Now, with this kind of initialization, how my filter is going to behave? My filter will be behaving like a sharp decay. When you plot, if you plot a Monte Carlo run or even a single run error also, if you initialize this, your filter, when you see your P matrix after a single run, your P matrix will be coming a sharp fall it will come. Why is this sharp fall will come? Because you have seen here I have divided it by delta t. Now, delta t is normally very less in a actual practical system. Suppose it could be 10 millisecond, it could be 20 millisecond. So, you can assume now 1 by t. So, millisecond. So, that is why your velocity initial error will be very large. So, your velocity error variance will, you have a sharp decay, which is okay, not a problem. But if you want to avoid it, there is an alternate way to assume that your system was initially stationary. So, in that case, you can presume your filter to be kind of using the second measure, the first measurement you can take, and x dot 0 0 is 0, or you can assume sometime Vmax also, some maximum velocity, the target, you can assume your truth is moving, either one or. So, I have made it or, that is also okay. So, this will give a kind of relatively stable this kind of a thing, okay, estimation error variance. It does not depend, Kalman filter does not depend on initialization too much, unless there is some problem, but 99.99% case it does not depend on initialization. You can choose whatever, but it is up to you to choose it judiciously. Okay. This is actually the filter initialization. So, once the filter is initialized, you can see now. Now, again I am just repeating once, just summary, time update, I am going to calculate my predicted measurement and corrected predicted Cartesian measurement I am calculating, then straight away I am calculating my R, each and every dt I am calculating my R from polar to Cartesian using the equation that I have shown. Then I am going straight away my measurement update, and the measurement, obviously measurement should be in, and then my cycle is repeating. So, this is a very simple example of 2-dimensional tracker of your Kalman filter, of your pseudo-linear filter. Same thing can be extended for 3-dimension also for radar. Here it will be r theta phi. So, range, azimuth, elevation, your elevation is also there. You can simply bring it to the polar to Cartesian. Okay. With this you can now run this pseudo measurement filtering approach. Okay. This is very important, even for automotive radar and all ADAS application, people does not prefer to use EKF or any non-linear filter, EKF, particle filter and all. Pseudo-linear filter is the best thing to use. Okay. So, with this, this is one part of pseudo-linear filter, it is not yet over. Now, I will take an example in my next lecture, I will take an example of a bearing angle only tracking problem. Bearing angle only tracking problem means, suppose now you are using an EOIR sensor, or you are using a say EOTM or electro-optic tracker, or even say you are using some passive RF which gives you measurement as far as direction of arrival of the signal. If that be the case, in that case you won't have range measurement, you will only have the bearing measurements with you. So, still can you use Kalman filter? We will see how we can use the pseudo-linear filter, we will see. Some case you can use, some case you won't be able to use. With this, now we will go to the bearing angle only measurement problem. Okay, first before I go to bearing angle measurement problem, the first thing here your Kalman filter, if you want to see that position and velocity RMS error for this 2D direct tracking problem, it is a representative plot, not an exact plot. So, but you will get something like this, similarly like this. So, this kind of exponential decay, and at the end you will see the error is kind of steady state error is kind of converging. Okay. The more and more Monte Carlo run you take, the more and more smoothness you will get. In a single error, it will be jig, 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 jig. Okay. It will be jig, 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 jig. The more and more ever this thing run you will take, the more and more RMS error you will calculate, or error standard deviation, whatever you calculate, you will get simply some stable this kind of thing. Okay. This thing will go away. Okay. So, this is the position velocity plot just now I have shown. So, with this already I have discussed that how even if you take more and more Monte Carlo simulation, how your steady state error is kind of going to be smoothing out. So, it will the more run you will take, the more your RMS error will be smoothing out. Normally, you can have this kind of signature for your position error and velocity error. So, I would like to tell two more things. First of all, bearing angle tracking is altogether a different subject. Even if you mostly it is used in underwater tracking or underwater systems, mainly for submarine tracking. You use your sonars. You have even your ship also you have your sonars. So, sonars using the sound waves and the direction of arrival, you calculate your bearing angles. Okay. Even UIR camera UIR also can give you bearing angles. Now, the problem is that you are getting, so you have now only the azimuth measurement, say a 2D problem. So, you have only theta measurement. You tell me, and you do not have range, how will you estimate x and y? It is not possible. It is not possible. Since you have two unknowns, x and y both you need to estimate. X dot y dot you leave it, they are derived variables. X and y you have to estimate, but you have only one equation. You cannot estimate it, okay, unless you know something, unless there is some information is given to you. Some range constraint is given to you. For example, in submarine tracking or any kind of underwater tracking, you have to have some kind, what people used to do some kind of maneuver with your own ship with respect to the target. So, this is your say own ship trajectory, and say this is your actually say the target trajectory. So, that you at least head on to a constant kind of a line of sight, which is actually known to you, so that you get some derived range information, then you can do the tracking. But if this constant, normally it is not equal to, it should be less than equal to or some within some bound, but at least you have some kind of range information. This own ship maneuvering is basically done to make the constant line of sight to the target, so that at least you get some kind of passive ranging this thing. Even for aircraft tracking and all, ground UIR you have a LNR, so that some kind of laser ranger. So, with that laser range finder LNR. So, with this at least you have some range information. Option 2, this is one part. Option 2 is that suppose you do not have LNR, or you cannot, your ship cannot do maneuver with respect to the target, then what you do? Then you need to have a second option. The second option is called, you need to have multiple UIR payload which are looking for the same target. So, you have a theta 1 and another sensor which is giving you theta 2. See, I cannot write both A and this thing. So, which is giving you theta 2, then, and both are looking at the same target, then it is possible. You can do some kind of triangulation, you have two equations, you can calculate x and y. Okay. So, this is actually possible. Okay. So, theta 1 and theta 2, with this two you can at least make this thing work. Okay. So, this is the thing. Now, next lecture what I will be showing, I will be taking a very interesting problem. Again we will solve a problem. Now, all we will do, we will not go to theory much, we will only solve some problems, and these problems will be a part of assignment as well. So, this problem we will take a bearing angle only this thing measurement, and we will see how, and one dimensional or two dimensional only, not a three dimensional. So, elevation is not there. So, with this how the things can kind of change, that we will be kind of encountering. That is why. So, now what you have to do now? You have to we will take an example which will tell you that how using only the theta measurements, and obviously I have to know something else, then I can do. Another example I would like to give, because before going to the lecture 10, I would like to give some practical things, so that at least where actually this theory is getting used. Suppose now an UAV tracking system, you are having a UAV is having a UIR camera. Okay, with this you are doing some surveillance. UAV is so what will be now? Your UAV will be UIR will be giving you tan inverse y relative by x relative, and your sorry, phi will be your actually tan inverse z divided by x relative square plus y relative square. Okay. Now, this z is replaced by h. H is what? H is actually your AGL, altitude, from your UAV to the ground, okay, or it could be AMSL also, that does not matter. This information is known from where? From your vehicle or UAV navigation system. Your baro altimeter, your GNSS altitude, something is giving you this H value. Now it is fine. You have now, you can estimate your X and Y. You have two equations. So that is what my thing. But if the Z is Z, if both are, if you are taking an airborne target, again you have to need a either multiple UIR or some kind of passive ranging you need. Okay. So, with this kind of introduction, I would like to now stop this thing, and I would like to go to the lecture number 10.